Nice to meet you all, except some of you who I've met. I mean, it's still nice to see you. So this is predicated on the fact that after that hour, you now care about amenable groups. I hope you do. Okay, so let's so heavy. Okay, so this is a part of this area called measured group theory, which I hope you care about because that's what the week is. Okay, so measured group theory is roughly, for now it's going to be this. Oh, so maybe let me just do some assumptions, which I assume are going to be true this week, but I don't know, we'll see. Okay, so gamma is always going to be a countable discrete group. I've never seen a topology on a group before. I don't know how that works. X is always going to be, okay, so for this, but maybe not all talks, I don't know, but for today, X is always going to be a probability space. And if maybe I'll refer to a measure and it'll be called mu, so it's going to be X mu. But I don't want to keep writing mu. And also, I don't really like writing mu. Just, I don't know, it's kind of weird. So I'm just going to write it as X. And okay, and then if maybe I'll forget to say, is it good? Should I fix something? No.
Color choke. Yeah.
Color.
Oh
yeah. No worry. Okay. So we've got these things going on, and okay, sometimes I'll talk about functions, and they'll all be like Borel functions if I ever forget to say that, because I also don't know what that looks like if it's not Borel. Okay, so the point of measured group theory is to study groups. So when I say groups, I mean countable discrete groups. Study groups via their actions, and by this I mean Borel actions on probability spaces. And by this I really mean standard probability spaces, because I also don't know what it looks like when it's not standard. Okay, so this is the first approximation. This is what this entire week is about. Okay, so we need some actions, otherwise you won't care about this. So okay, so here's some actions, which I will refer to. Okay, so the first one is it's called irrational rotation. So this is the action of Z on S1, and it's just you just take any element, any angle, and rotate by it. So I'm just going to fix one for the purposes of today. It's going to send X to, okay, sorry, I'm thinking of this as R mod Z. It's going to send X to X plus your favorite irrational, root 2, maybe everyone likes root 2. Okay, so that's called irrational rotation. So if you take a rational rotation, then everything will just come back to itself. Like if you rotate, if you add, I don't know, 1/10, it's going to just come back to itself after 10 things. So every orbit's going to have size 10, which I don't care about. So I want the other one. I want anything where the orbits are infinite, which is exactly an irrational rotation. Okay, so this is interesting. Maybe you care about other groups, like me. So in that case, you can take this thing. It's called the Bernoulli shift. And this is somehow very important. It kind of sees, oh, sorry, the measure here is Haar measure. It's the unique measure you know on S1, which is the definition of Haar measure. Okay, Bernoulli shift. So this is if you take any group now, it acts on 2 to the gamma. You can think of it as subsets of gamma. It just translates it, or you can think of it as this, precomposition. You can think of it as a function from gamma to 2. It precomposes any action you make on here. Any 2 actions that 2 different people in this room make on here will be the same one. So take that one. That's not true. There's 2 of them, but 50% of you will do one, and 50% of you will do the other. Okay, and then the measure, I'm just going to take the uniform measure on 2, and then just take the product of it. So I'm just saying the probability of the 5th coordinate being 0 is a half, and except replace 5 is a variable. Yeah. Okay. Okay. So that's this is an interesting action, and then let me just sort of give you a nice class of actions, because maybe I'll keep referring to this, and it'll be good to sort of have a thing. So if you have a countable, let's say you have a countable subgroup, compact group. Because I actually do know some other groups. So this is a countable subgroup, and this is a compact group. Then you can just consider the action, just the left multiplication action. So gamma dot G is gamma G. So it just multiplies on the left. So the equivalence classes are they're the right cosets of gamma. And it's a compact group, so it has a Haar measure. So actually the first example is a special case of this, right? Because S1 is a compact group, and then you just take any cyclic subgroup of it. I mean, like infinite cyclic subgroup. You can also take the finite one, but it's not interesting. Okay, so I'm mostly going to be talking about these actions and maybe a couple other ones, but maybe I'll motivate them later. Okay, so these are all actions on probability spaces. So, and in particular, these ones are all actually a bit nicer than just being actions on probability spaces. But it's an action on a probability space. I just mean it's a Borel action. I didn't mean that it had to preserve the probability measure, but I do want to talk about that. So, okay, so an action is PMP.
Forte,
Yeah.
can I ask you to nevertheless define the shift action just in case there's anyone?
Yes.
You know.
Yes. Okay. So gamma, if you consider it here as a function from gamma to 2, then gamma of a different thing, delta, is f of gamma inverse of delta. I guess the way you should think about it is gamma of f and gamma of delta is f of delta. Yeah. Okay. Anyways. Okay, so action on a, so this is a probability space, is PMP. So I think Riley said this, but let's just write it down. So it's probability measure preserving. If it preserves the measure, so if like it preserves the measure, so okay. And I just mean that thing that he wrote. So it's just if you take gamma of mu. So if you take the measure of a set shifted by gamma, it's just the same as the measure of the set. So if you take a subset of S1 and you rotate it, it's not going to change the measure. If you take this thing, it's not going to change the measure because you're just shifting the coordinates, and I took the same measure on each two. And that is also not going to change because of, I don't know, like reasons, because our measure is unique, I guess. Okay, so these are all all the above are PDT. So somehow, like in measure group theory, a lot of the time you don't need to look at every action. You just need to look at the PMP ones, and that's like very sufficient for all your needs. Like you can still study a group by only looking at its PMP actions, and you don't really lose that much. Okay, so is that okay? That's actions. So I haven't even got to any of the title yet, so that's not good. Is there a clock? Am I the clock? I can do it. Oh my god, it's 10:22. Oh, okay. So now we're going to do equivalence relations. So now we're going to do measured equivalence relations. Eventually, I'll say like why we're doing this, but let me just give you some definitions, just in case I never get to them, because everyone is expecting me to give all these definitions. So I need to do this before the mini courses start. Okay, so here's one thing you can do. So let's say you have an action. So this is as always, it's a Borel action. Oh, gamma stands for some countable group. So it's a Borel action on a probability space. So given any action, you can make something what's called the orbit equivalence relation. So there's induces what's called an orbit equivalence relation. It's exactly the equivalence relation where the classes are the orbits. Yeah. So equivalence relation. And everyone's going to keep saying orbit equivalence relation. So good to know. Okay, and I'll denote it like this. So it's it's like missing some information because it doesn't have the action in it, but that's okay. Forgive me. And this is an orbit equivalence relation. So this is an equivalence relation on X, where two things are equivalent if they're in the same orbit. So defined by X is related to what's called X prime. X prime if this is the definition. So it's defined if and only if there exists an element of the group sending one to the other, such that gamma of X is gamma prime. And so I'm kind of lying here because everything is an action on a probability space. So all the functions are actually like equivalence classes of functions up to measure 0. So so you sort of like fix one function for each of these, and then this will be an orbit equivalence relation on a measure 1 subset. So everything is sort of up to measure 1 here, and it's going to be really tiring to say everything is up to measure 1. So maybe that's another thing here. Everything is up to measure 1.
Up to measure 0.
Yeah. It's like it's the filter. Sure. Yeah. Let's do the ideal. It's up to measure 0. Yeah. Okay, so is this okay? Okay, so now I'm going to define what well, okay, so this thing is this is an instance of measured equivalence relation. So now I will like say precisely what that is. So let's say what that is. So okay. So measured equivalence relation. I'm going to just start writing it like this because I'm running out of time. So a measured equivalence relation is an equivalence relation E on a probability space X such that, okay, and then there's two equivalent things. One is just that it comes from one of these, and the other is some sort of abstract condition such that, like, okay, either of the following holds. So these are equivalent characterizations due to Feldman and Moore, I guess. So one is just that it comes from this. One is that there exists a Borel action of some countable group. So there exists a countable group and there exists an action such that E is just equal to that thing. And the second thing is a sort of abstract thing. So it's that E is Borel. And by Borel, I mean as a subset of X squared. So, okay, an equivalence relation is just a set of pairs, right? You're just saying which pairs are related or not. And I want that set, so it's a subset of X squared. I want that set to be Borel. And every equivalence class is countable. Equivalence class is countable. Oh no. So this is called a countable Borel equivalence relation. Okay, so for like people that are familiar with this, it's just a countable Borel equivalence relation on a probability space.
These are equivalent conditions?
Yeah, these are equivalent. So this is trivial, and okay, this is trivial, and then this is a theorem of Feldman and Moore, and this is actually not that easy. It uses a countable sections uniformization theorem from descriptive set theory. Oh yeah, and the thing is that I do descriptive set theory. I'm not like a measured group theorist, so yeah, I don't know what the point of that was, but now you know. Okay. I guess the point of that is that I'm going to maybe talk about things a bit more combinatorially than some of the other people might. Okay, so this is a measured equivalence relation. And so basically I'm just saying anytime you have an action, so we're always just going to have actions. And I don't think we'll ever have ones that don't come from actions, at least like right now. So, okay, the question could be like, why are these things, like, why are we looking at these things? Because, you know, they all come from an action, so why don't we just look at the action? Okay, so first of all, let me tell you what it means for them to be isomorphic. So measured equivalence relations. So I haven't like looked at the audience here. Questions? No. Okay. Measured equivalence relations, E on X and F on Y are isomorphic. So the point is that the isomorphism doesn't remember the action at all. Isomorphic. And there's sort of looser notions that also still don't do this. If the obvious thing holds. So if there exists a Borel map, which is a measure isomorphism. So these are probability spaces now, right? Because everything is. There's a measure preserving isomorphism, like a measure isomorphism. So it just sounds, you know, like these spaces, these underlying spaces have to be isomorphic. I mean, there's only kind of one space, but anyways, there's isomorphism, which takes this equivalence relation to that one. So there's a measured isomorphism such that for all x and x prime, these are related if and only if their images are. And by for all, I mean for all x in a specific co-null set. It's like for all mu. For all mu.
Yeah. Maybe before we think it's too like maybe write a book like a measure isomorphism theorem or something so that they know it's not about x and y being different.
Oh yeah. Okay. There's only one standard probability space. Yeah, I guess is atomless isn't the definition of standard. Okay, it's an atomless standard probability space up to isomorphism. Standard means it's not too big. Standard means it's on a polar space. Okay. Okay, so the point is that this isomorphism doesn't see the group action at all. And this, so it's good, right? It forgets a lot. It forgets a lot of the action. Well, maybe it's bad. You're like, oh, it's bad. It forgot the group. But actually, it's good because so the good part about this is that I don't know. I mean, I'm inventing this now. There's no algebra. Yeah. I'm bad at algebra. I hate algebra. I do algebra. So the point is that algebra is too restrictive. So maybe let me give a sort of instance of this. So Riley talked about this. So there's this von Neumann conjecture. Okay, so we want the following. So we want the following fact. So every group is either amenable, or contains F2, the free group on two generators. Right. So this would be nice. Okay, unfortunately, this guy Olshansky that refuted the von Neumann conjecture. So Olshansky constructed a non-amenable group with no F2 subgroups. So no subgroups isomorphic to the free group on two generators. So okay, so this is so we want this, but it's not true. So anyway, it's is there no more white chalk? Oh. Yeah. Oh, okay. I used the one from the grammar. Okay, so we want this, but unfortunately, this is not true. But I didn't really say what contains F2 means. I don't know, it means anything. Okay, so it turns out this is true. This is true. True. For some definition of contains. Okay. Maybe I'll tell you the definition now. Yeah. So okay. So what I mean by contains F2 is the following. So let's say if you take this as the definition. So gamma contains F2. F2 is there exists let's see, there exists free PMP action of gamma. Let's call it gamma acting on X, and a free PMP action of F2 also on X, so some space X, such that the equivalence relation here is contained inside. So there's a space X. There's a space X. There's some action of it by gamma. So these are the gamma orbits. And there's also an action of F2 inside here. So this is the F2 orbits. So this is true, and I guess it's due to someone in this room. So I need to put the name now. Okay, so this is true. This is a theorem of Gaboriau and Lyons. So this is what's called the measurable solution to the von Neumann conjecture. So this is the von Neumann problem or something. Apparently, it's not due to either of them, but okay, well, that's a separate thing. Okay, so this is a good reason why you would want to care about amenable equivalence relations, even if you only cared about the groups, because some fact about groups, which we want to be true, now is true. Okay, so of course yeah.
Well, do you know when the result of Olshansky is from?
No. Yeah, 80. 80x or 80b?
0.
Oh, x is 0. Very good. Okay. So yeah, so this is the reason why you might care. So the point is that this F2 action inside the gamma action doesn't they're not related at all. It's not like the generator, each generator here goes to an element of gamma. So each element here did go to a generator of gamma, it would work, right? If gamma has an F2 subgroup, you can just take those two F2 generators and get exactly this picture, right? But the point is that even if gamma doesn't contain an F2, you can still find an F2 action which maybe doesn't respect the individual group elements, but it still respects the equivalence relation. And this is good enough for reasons that I haven't got to yet. So Okay, so maybe one problem that you might think is that if you take the group and you take the action, and then you just look at the equivalence relation up to that notion of isomorphism, maybe like everything is isomorphic, right? So okay, let's talk about some isomorphism invariants. So there's a couple obvious ones which are not so interesting. So one is like the number, the amount of classes. A class in the equivalence class of, I don't know, of size 8 or something. I mean the measure of points for which the orbit has size 8. So that's invariant under isomorphism because the isomorphism still respects the sizes of the classes, right? Okay, but maybe all your classes are infinite, so this is like not interesting. And oh yeah, okay, I didn't say. Okay, so one thing that's true is there's a notion called TMP for equivalence relations, which I guess I should define. So whether it's probability measure preserving or not is an isomorphism invariant. So let me say what this is. So a measured equivalence relation E on X is PMP. So also probability measure preserving. Yeah. So because there's a probability measure here, right? So it's PMP if for every Borel function. Okay, so the idea is this: you have your equivalence relation E on X, so the equivalence classes look like this. The statement is that if you take a bijection, which just stays within each class, so it doesn't like move the classes around, then it should also preserve the measure. So if for every Borel map T from X to X, which stays in each class, so such that for all X, X is E related to TX, we have that the measure is preserved. So T, like the push forward of the measure under T is the measure. So I'm just saying if you take T of a set and measure it, it doesn't change the measure at all. And then maybe, okay, follow up fact. Okay, like follow up. All right. Oh, sorry, every like Borel bijection, let's say. Yeah, every Borel map. Yeah. Every Borel bijection, yeah. Okay, so here's a fact, which it's like an exercise for, I don't know, there's like problem sessions, do they exercises in them? Okay, so here's a fact. So let's say you have gamma acting on here, it's a probability space. Okay, then the action is PMP. Is PMP in the previous sense, if and only if this equivalence relation is PMP. So PMP is really not a notion about actions at all. It's really something you can already see from the equivalence relation level. So this direction is like immediate, or no, this direction is immediate because these gammas preserve the classes, right? Because that's kind of how the classes are defined. So there'll definitely be a bijection where everything is related to its image. So what's not obvious is that if you take something which doesn't come from a group element, like why would it still preserve the measure? And the reason is that they still kind of do come from the group elements, like if you break it up. So it's an exercise. Okay. But there's something to check here.
Before you erase what you're erasing, I was really hoping you would say your joke here, but I guess you.
Which one? Why is this character get no prize because I was standing in this field? No.
The one about Borel names, which was Armand and Daniel.
Oh yeah. Like, sure, yeah. It's yeah. I hope it was good. Okay, so being TMP is also a property of an equivalence relation. So it doesn't, like, two things are isomorphic, just if you like follow through the definition, they'll still work. So, okay, so somehow like this still doesn't really help because, like a lot of people in this room only care about PMP equivalence relations. So they're like, sure, okay, everything's PMP. And then they only care about things with all classes infinite. So they're like, okay, so they're like everything is all infinite classes. So, okay, let me tell you an actual interesting one, which is amenability. So let me add two things to this list. So one is called amenability. So I have to define this, and one is called hyperfiniteness, and these are actually the same, but like, they're kind of, in my mind, they're different, but then they just happen to be the same. So there's only one thing here. These are going to be the same, but this is a hard term. Okay, so.
I'm going to also mention ergodicity.
Oh yeah, I guess there's on it. Yeah, there's something called ergonic. which I don't know how to define it. You can define it in words. So as an equivalence relation is about every set which is invariant under the group action is either measure 1 or measure 0. And in general, like every equivalence relation you have splits up into a bunch of ergodic ones. There's something called ergodic decomposition. So they're kind of like the smallest, like the connecting, like the components of irreducible versions of these things. Okay, yeah. So the reason I need to do these is because so here's something that might not be obvious. Okay, like not obvious fact. I don't know if it's
the invariant there, the ergodic components.
So saying it's ergodic at all is definitely an invariant. Yeah, you could also say the number of ergodic components. That could also be a thing. Yeah, that works. Maybe you could talk about like the actual ergodic decomposition, but then you have continuum many. Yeah, maybe. Yeah. Okay, so here's something that's true. Okay, true fact. But maybe not obvious. So, and it kind of talks about what Riley was talking about, which is that if you take this irrational rotation, so this is irrational rotation. Okay, so then this thing is equivalent to something which I just realized I haven't ever defined, so that's a problem. Okay, so this is equivalent to something that's called E0, which is sort of the most important equivalence relation in this field. So now I will define it for you. Okay, so there's an equivalence relation called E0 on Cantor space. Omega is the natural numbers. Yeah. Oh, why didn't I just write that? I don't know. Okay, so there's an equivalence relation here, and with the same uniform measure product measure, defined by. So it's called eventual equality. Okay, it just says that two sequences, as I'm thinking of them as infinite binary sequences. So they're related if they're after some point they're related. So there exists a point, and then after that point they're equal. Right. So if you just take like 0, 0, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 0, 1, 1, 1, 1, 1. So they're equal after this point. So they're related. I guess maybe one thing to note is that I didn't define this via a group action. So and you're allowed to do that. I mean, it still satisfies abstractly. So every equivalence class here is countable, and it's Borel. It's a what is it? It's a sigma. It's an F sigma. It's K sigma. Yeah, it's an F sigma. So yeah, so it's definitely Borel. And okay, you can also see this as this countable subgroup of a compact group if you want. So you can think of it as which is kind of my point here. So you can think of it as this space as just Z mod 2 to the omega, right? So just countably many products of this, and you can think of this as the countable direct sum, which I don't know. People talk about it like they denote it like that, or maybe they denote it with a little plus, or they just write out all the infinitely many terms. Or okay, so there's a countable subgroup here just consisting of things that are eventually 0. And this is a countable subgroup of here. And if you take the coset equivalence relation, you get exactly this. And okay, the point is that these two, okay, so this is called E0. And these two things are isomorphic, right? But these groups, this group generates this action and this group generates this action, are definitely not like, that one's like locally finite and this one is Z. So yeah, and that's kind of Raleigh's point, right? It was like everything is just the same as all immutable groups are just the same as Z. So this is an immutable group. And this is Z. So, okay. So it falls into this sort of picture. Okay, so that's nice. So that was like a non-obvious isomorphism. And then you still might think that everything is isomorphic. But then, like, okay, we'll show that something is not isomorphic. So in particular, any action knows F2, like the Bernoulli shift or something.
We forgot to mention that finite groups are amenable, and this is an increasing union of finite groups.
That's true, yeah. So it's locally finite, so it's an increasing union of finite groups, and that's good. That's like it's like a hyperfinite group. Oh, okay. Okay. So let me define what an immutable equivalence relation is. So measured equivalence relation E on X is amenable. If there are writer functions, which is sort of just it's the easiest version of the definition which you can write, but there are other ones. So if there, if there's a sequence of writer functions, which I will make precise, and then Yeah, so remember, like, the idea for writer functions is that on every, okay, well, let me say it in this case. So on every class, you want to pick a probability measure. So for the group, having a writer function means on the group you want to pick just a probability on the measure, or a probability measure on the group, which is kind of invariant under shifting. And the idea here is that if you have this, like, you have this equivalence relation, then you have all these classes. This is somehow not a great picture, by the way, because they're all supposed to be like countable, and the set is uncountable. So they're supposed to be like little, like thin. They're all supposed to have interiors. Anyways, okay. So on every equivalence class, I want to pick a probability measure. But the problem is that like if you could pick a point out of each class, then you could sort of trivially pick a probability measure, because you could just say, everyone just do what this person does, what that person picks, and then it'd be fine, right? But the problem is that you can like never do this. And so, for example, in this case, you can't pick an element out of each class. So you want to do something slightly weaker. So you want to.
I sure can.
Huh?
You can pick a point from each class, but then you get a non-measurable set.
Yeah, let's say you can't do it under 80 or something. Yeah, you can't do it in any reasonable sense that will give you a Borel map. Let's say. Okay, so you want to like kind of pick a probability measure. So the best you can do is that you can sort of approximate, get the sequence which is approximate, and it sort of converges towards picking a probability measure, which is what writer functions are. So it's, if there's a sequence of writer functions, so so Borel maps, let's call them Q, which sending each x, qn. So it's a sequence. Sending each x to a probability measure. So it's a countable set. So I'm just saying pick a mass for each point. So a probability measure on x, the class of x, which is the notation which I just introduced. It's the equivalence class of x. So each x tries to decide what the probability measure here should be. And you kind of want them to all agree. And this is the sense in which they're going to agree. So the Borel maps sending to a probability measure such that, so it's a probability measure like Q and X, such that if you take 2 points in the same equivalence class, eventually they'll start agreeing on what the probability measure is. So such that if you take X, such that if 2 things are related, then this limit, so if you take the equivalence, if you take the measure that X decides on at the nth time, and you take the measure that X prime decides on at the nth time, they converge to 0. So sort of, if you want them to be, they're going to be very close at time 1,000,000. Okay, and then so by a Borel map, I mean the map, like, so it, for every pair, so if you send every x to a probability measure, you're sending x to a function that takes a y and then outputs a number, right? So I'm just saying the map that sends each pair to this is Borel. So that's an amenable equivalence relation.
Maybe for clarity, can you write like, I don't know, x prime goes to q sub x?
Yeah, the map sending x, y to q and x of y. But in any reasonable sense that you define Borel, it will be Borel. Okay, so this is an amenable equivalence relation, and my claim is that this has a very strong connection with immutable groups, which, other than that, the definition looks similar. When I got until 11?
Yeah, 8 minutes.
8 minutes?
No, 10. How about 10?
Sure. So okay, so here's a fact. So okay, let's say gamma is a group, and then you fix an action. So this is a probability space. Okay, then the following are equivalent. So if you have gamma is, well, okay, well, the following things happen. Okay, so let's say gamma is amenable. Then this equivalence relation is amenable. And maybe this is an exercise or something. So if you want to, okay, let me just draw the picture. If you're on an equivalence class, you're at an x, And I want to know, so I'm in my equivalence class, I see all these other things in my equivalence class, and I want to know like what the weight should be. Well, okay, everything, I mean, by definition, it's the orbit. So everything has a bunch of group elements which send these here. And then there's some group elements sending these things here. There's some group elements sending these things here. Right, and then I know that all the group elements added to one because like I'm assuming I have random functions for this, sorry. So I fix a random function for the group gamma. So there is a probability measure on the group. So like the sum of the outward arrows is 1. So okay, so how about I just say the measure of this is the sum of these arrows, and the measure of this is the sum of these arrows, and the measure of this, and then they'll just add it to 1. So that's the proof of this direction. And the other direction kind of can't be true for obvious reasons. Like if you take an action and it's like trivial, then that thing's amenable, because you should think of amenable as somehow being easy. So if you take an action and it's trivial, then it's amenable, but obviously like, every group has a trivial action. So you need to sort of make a non-triviality condition, and it turns out this is the right one. So this holds if maybe let's use a different color. So this holds if the action is free PMP. So if this group action is free in PMP. Okay, but then if it is free in PMP, this is easy to prove. You just say, what's the measure on the group? Well, every point in my space has chosen a measure, and then I can average them because the entire space has a measure. And the reason the averaging works is precisely because it preserves the measure. So that is also an exercise. Okay, so this is good, right? So in particular, so like since every group has a free PMP action. So this is the Bernoulli shift. So the Bernoulli shift is free on a set of measure 1. So and everything is up to a set of measure 1. So it's free. So this one, like the orbit equivalence relations C amenability. So in other words, you can tell if a group is amenable just by looking at the collection of all of its orbit equivalence relations. So, okay, maybe more precisely, maybe I'll make it precise because that's important. So what I'm saying is that gamma is amenable if and only if gamma has a free PMP action with this equivalence relation, non-amenable. It's non-amenable. Yeah. True. Yeah, it's the exact opposite of what I said is true. That's great. Okay, so you can tell whether a group is amenable, but just by looking at all of its orbit equivalence relations, which is good. Okay, so how much I got like 3 minutes left? Okay, so let me just talk about hyperfiniteness for a bit because that's also important. Okay, so for example, this shows that if you take the action of F2 on its Bernoulli shift, that thing is not amenable, just because you can push the amenability back to the group, which wouldn't make sense. Or if you take F2 as a subgroup of a SO3 or something, anything you want. Okay, so now everything is measured equivalence relations. So I'm just going to write E on X. So E on X is hyperfinite. Hyperfinite if there exists an increasing sequence F0, F1. So this is an increasing sequence of equivalence relations, finite equivalence relations, like Borel equivalence relations. Finite meaning every class is finite. Okay, such that E is just their union. So E is the union of a bunch of. So if you think of it as a group somehow, like the group equivalent of this is that your group is locally finite. And the sort of big punchline of who is it, Kahn, Feldman, and Weiss is that that's the exact same as amenability. So amenability is somehow like local finiteness. So hard theorem is that E is amenable if and only if E is hyperfinite. So
mentioning almost everywhere.
This is hard. Oh yeah, but everything is almost everywhere. But yeah, true.
Particular
This is
theories were.
up to like null sets. Yeah. Yeah, I would say this is false, but I mean, anyways, it's true. Okay, so this is okay. So I guess the point of this is that somehow, if you know something is immutable, you should be really using this fact because this is a much stronger property. And if you wanted to show that something is like not immutable, then you should be, you should be doing the other one. Like it's easier to show that it's immutable, but it's easier to use that it's hyperfinite. Okay, so if you ever need to do something, this is that. Am I out of time? Should I?
No, you have time to at least credit the people in this theory.
Oh yeah, it should do that. It's not too hard. Okay, so this is due to Kohn-Feldman noise. So there's a proof in many places. Andrew's website has a good one. Okay, this is called Feldman noise. Yeah, and it's kind of like, I guess the proof is similar to that like proof with the layer cake that Riley did, except it's like a harder version of that. But somehow you want to take this thing and then sort of get these finite sets out of it. It's a similar sort of proof. Okay, so that's it. Yeah.
Okay, thanks. Any questions?
Mm-hmm.
Can you explain again why this is like the sequence of writer functions, like the analogy?
Yeah, I can just write down the group definition. So a group is amenable if there exists a sequence Pn of probability measures on gamma such that for all gamma and gamma, if you take the nth probability measure and then you take the nth probability measure shifted by gamma, it goes to 0. So these are the same idea. And these both generalize to one thing. It's a groupoid thing. So yeah, the point is that like there's only like I don't know if you know like in groupoids, like there's only one point here. So when you act by gamma on the point, it still goes to the same point. So that like x is related to x prime, right? But somehow you've also like moved the measure around by the gamma.
Other questions? Okay. If there are none, maybe I can tell for a joke.
Sure.
I just want to emphasize that theorem rather than the joke, but the joke is no longer funny because I can say the theorem was that you're given some abstract equivalence relation, which I draw the classes like Forte classes, continue many of them, each class is countable. It's an abstract P. All of a sudden, the theorem says that there's a group action, there's a group and its action on X. This is X, such that this group is what creates these classes. Okay, so like for each point of X, this gives a way of referring to its friends by these like gamma elements, and these gamma elements are Borel maps. So like with the gamma prime and so on. So I don't know what context we were at. We were like at some coffee shop. So I was like, yeah, when I give a talk, I really say that this theorem gives a way for each point to refer to its friends in the same class by names, by Borel names, and then for that goes Emil, Armand, and then so that was the joke, and that's the theorem.